Okay. All right, we should be recording. Okay, so an alkene, so what does that mean? Double bond between two carbons. All right, just checking. What? Alkene, C double bond C, is treated with OSO4, osmium tetroxide, followed by hydrogen peroxide. When the resulting diol, so that means we're going to get a diol, right? Okay, we don't know what's there. Okay, that's the question. Is treated with HiO4, the only product obtained is an unsubstituted cyclic ketone with the molecular formula C6H10O. And you know that it's cyclic, an unsubstituted, and a ketone. So what is it? What is the cyclic unsubstituted ketone with formula C6H10O? What? A cyclo who? Hexanol? Is that what you said? Well, that would be an alcohol. Okay, this is a ketone. Okay. Everybody agree? 2, 4, 6, 8, 10. There's 2. Okay. All right, now, so what do you think the structure of the alkene is? It's like a little puzzle. You got to get good at puzzles. That's what chapter 12 and 13 are, puzzles. All right, so, well, I'll just make this a random one. Okay, let's just put methyls there. Okay, I'll just put methyls there. When I do that periodic acid thing, that's gonna cleave it right there, and you're gonna get to what? What do you get from the left side? What do you get from the left side? CH3, and then what? What? Nothing? The other methyl's there. Okay, what happens to the carbon that had the OH on it? It becomes a what? Yeah. Okay, what happens to the right side? Oh, I'm going to get the same thing because both sides are symmetrical. Okay, that's called a clue. This happens to be acetone, just FYI. All right, so if this is the only thing we got, what is the structure of the alkene got to be? Okay, what do you mean? Don't be saying I don't know. You got to figure it out. There's your clue. What is the carbon of the carbonyl come from? Okay, so what has to be here? Right? So the diol would have the 2 OHs and then it gets chopped. Okay.
So that's the alkene?
Yeah, that's an alkene. You can have double bonds between rings. It's okay. Okay. It looks illegal? Okay. So, what would you get from this one? What starting material would give that as its product? What do you think? Okay. Instead of drawing pictures, I wrote out the names. Sometimes I'm like that. It's easier. So just figure it out and then look for the name. All right, I'm up to 17. You got it? Okay, I got every answer except E. Why did I get an F?
What?
That was me at the last minute trying to see back in. It hit it.
Well, we don't know if D's right yet. Let's figure it out. All right, so how did you approach the problem? Okay. What did you say? Something about you thought it was a ring? What was your clue that it was a ring? There's 2 carbonyls in the compound, okay? And every answer has that in it, except for F. Okay, so how are you going to put it together and make it a ring? What are we going to do? Hang on, you get a purple. Okay, so what can you tell me about this carbon and this carbon? Where do they come from? They're double bonded together. Very good. Okay, so I'm going to count from one carbon to the other, and that will tell me how big my ring is. Agree? All right, here we go. 1, 2, 3, 4, 5. Right? Those are the 2 that are double bonded together. Okay, so what size is my ring? 5. What does it have in it? A double bond. Okay, so is that it? Is it cyclopentene? No, because the methyl's missing. Okay, this carbon is missing. Where does it go? On what? The double bond. Okay, because this carbon, I'll just call it 1, is this one. Okay, this one is 5. This is not for nomenclature, just for labeling. Okay. What else is attached to that 5? A hydrogen, but you don't have to draw it in. Okay, so what's the name of that? Yeah. Okay. You remember all the nomenclature rules, right? I'm sure you do. Okay. Oh, apparently I got to do that. Okay. When you are trying to reduce alcohols, we talked about making the alcohol double bond and then adding hydrogen. Okay? Well, somebody figured out, I often wonder if it was by accident, that they would convert it to the tosylate and then add lithium aluminum hydride and reduce it. Okay? Because this is such a good leaving group, they could get away with it. Isn't that nifty-galifty? Okay? It works with most, don't you love it when they say that? Most primary and secondary alcohols. Doesn't work good with tertiary alcohols. Why not? What do you think is the reasoning it doesn't work good for tertiary alcohols? Remember that little rule? Okay. No SN2 on tertiary centers. The hydride won't come in and substitute for the OTS minus. And if you get to the carbocation, you're going to start getting elimination. That's why it doesn't work. Okay. What products would be formed from the treatment of the alkene below? From the treatment of the alkene below with OSO4, H2O2 followed by HIO. So what do you get from this one? Can you see it good enough? All right, here, I'll make it dark. Yeah, this is, there's the alkene, it's right there. That helps. It even looks a little small, doesn't it? This time I'm going to ask you, Andrew, to make sure you got the answer you want in there. Okay. Okay, I'll do it again. So if through it. Okay, all right, Andrea. Okay. Okay, let's see. So I'm going to take this and I'm going to cut it, right? Okay, where am I cutting it? At the double line. Okay, so this carbon up here has an ethyl and a hydrogen attached to it, right? So what does that mean that it becomes? N aldehyde. Okay, what happens to the right side? That's a ketone, and the ketone is on carbon 2. That's this carbon right there. Okay, I don't want it to look like a, I'll make it a star now. I don't want it to look like a fruit. Okay, so which one is it? Okay, you get the carboxylic acid if you do a different method, like the fermentation. That one, okay, that was at least a good choice. Okay, so a Pinacol rearrangement is a unique reaction of a vicinal diol. So what does that mean, vicinal diol? Well, what does the diol part mean? 2 OHs. What does vicinal mean? Adjacent, yes. So if you forgot that, write that down so you'll review it. Okay, overall, it's actually a dehydration. So here's our Pinacol right here. Okay, Pinacol is a common name for that compound. I have no idea how to do that. But it's 2,3-dimethylbutane 2,3-diol. Okay. All right, notice the difference between this and the product. We lost, and what? Oh, that OH is gone, right? What else did we lose? A hydrogen. Okay, there's the water that's gone. But what else happened? The methylment. Right, see that? We had a methyl shift over. So what does that tell you has to happen? You have to make what in the mix? A carbocation. Okay? All right, let me see if I've got it. Oh, look at that. It's already done. Do you have the slide? Oh, you have to fill it in? I gave it to you blank?
Well, you gave us the starting.
I did? And the product down the bottom?
Yeah.
Oh, that was nice of me. All right, well, we'll go over it slow. All right, so the first thing that happens is it gets protonated. Okay, I just have H plus in there. This won't work if you don't have acid. Okay, you can use H plus or you could use H3O plus, in which case you would have to go there and then there. Okay, so you could do it either way. All right, if you like H plus, just leave. Okay, so now we have our alcohol that's protonated. Notice the thing is symmetrical. Doesn't matter which side you pick. Okay, all right, then we lose our water. Okay, so the electrons in this bond are going to go to the H and become the other lone pair. Why is it, it's like off again? Oh, those are the two lone pairs on the O. All right, notice what kind of carbocation we made. What kind is that? Tertiary. Anybody going, heck, I thought that was the most stable. Well, what happens is the lone pairs on the other O are going to come into play. So when this methyl migrates over, okay, you will get this carbocation, which is on a carbon adjacent to an OH. Excuse me, an oxygen with lone pairs. And those lone pairs are going to help stabilize it. Sometimes I've seen this step written like this, where it goes, that goes there and kicks that over. So that you go right to this. This is just another resonance form for that. Okay. So that's how come it does it, because of the second oxygen. Okay, so when you get down here now, you have this O, you'll notice, is protonated. So we're going to pull off the proton. Okay, the O has a plus charge, so water is basic enough that it can do it. Okay, water cannot pull off this proton up here, but it can pull off this one down here, because, so we're going to grab that, and then those electrons go to the O. That's how you get the ketone. See what we did. Okay, first we protonated. Remember, protonation is fast, 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 fast. Okay, if there's an acid in there, look for something to protonate. Okay, look for lone pairs, look for double bonds, look for minuses. Something was going to get protonated. Okay, so we're protonating this O. That gives us a good leaving group. And when water leaves, look what we get, a tertiary carbocation. Okay, so that's the start of it all. But then the other oxygen will come in and push that methyl over and stabilize the plus charge. Okay, so basically it's helping everybody out with its lone pairs, and then you deport. That makes sense. And it's kind of weird looking. This right here is the weird. Okay, that's probably the thing you haven't seen yet. Everything else we've done before. I am smelling food and it smells so good. Uber up. Do you smell it? Maybe it's somebody out there. It's those nurses. Oh, I'm thinking we need to visit the nurses. All right. Okay. Oh, you got a burrito. That was good. Eat it. Don't worry about it. Don't worry about the rest of us drooling. Where did you get it?
From my house.
Oh, I thought maybe you stopped picking it up.
No, save money.
Yeah, I hear you. I do that all. All right, esterification of alcohol. So the Fischer esterification is an alcohol plus a carboxylic acid. What one did you do last? Does anybody remember? You made pear, Okay, the carboxylic acid, was it acetic acid? Was this the one you didn't lab? What was the alcohol though? I don't remember. Was it 1-propanol? 1-butanol? It was a little one. I didn't think it was real big. And propyl alcohol? Okay, that's 1-propanol. Okay. The N just means normal. Just a regular chain, straight chain. Okay, so the alcohol plus the carboxylic acid, that's the one you made in lab, and you had to add sulfuric acid to it. That kind of gets everything going. The equilibrium is often unfavorable. Okay, so first of all, let's look at this down here and we'll talk about what that means. All right, so we have our alcohol plus our acid, and we're going to make our ester. They have determined that the O in the ester right here comes from the alcohol. The O comes from the alcohol. Okay, like by labeling studies, stuff like that, which you'll learn more about when we do chapter 12 and chapter 13. Okay, you'll see how you can use labeling to figure out stuff. Okay, so you'll notice that this OH and this H are gone. So basically, you got water as a byproduct of that. Okay, all right, here is isopropyl alcohol plus acetic acid. And you do this one and you make isopropyl acetate. Okay, you made propyl acetate. It's not isopropyl. Okay, all right, so you'll notice that there's an equilibrium here. Okay, see those equilibrium arrows? That means the reaction goes forward and it goes backwards. There's a lot of ways that you can help shove it to the right side. Okay, the most notable is to get rid of the water. Okay, you can get rid of that water and pull it out of there. What will that do to the equilibrium? It will push it to the right. Does that make sense? Remember doing the Le Chatelier's principle back in the good old days? Okay, so one thing that you can do, you can distill out the water as it's being formed. Okay, a lot of times you heat them to reflux. Did y'all reflux? I don't remember how exactly you did that anymore. What, you reflux? Yeah. Okay. You could reflux and you can put a special thing at the top that will actually touch the earth. It's pretty nifty by putting benzene in there. Benzene and water make an azeotrope. And it doesn't even sound like they should make an azeotrope, but they do. And they distill off at the same temperature, and it's a lower temperature than normal. And then once it distills off, they separate out. It's the weirdest thing. But you can use a little special piece of apparatus that will collect that benzene to get it off. So that's kind of nifty way to get rid of the water. You can put in something else to absorb the water, like a molecular sieve. Have you heard of those? Molecular sieves are these little round balls. They're made of molecules. They are made of molecules because everything's made of molecules. Okay, but they're made of a little polymer that is the right, and they have little pockets that are the right size to pull on. And you can put those in there and just have them stir, and then you just filter them off. That's another little trick. What did y'all do? Did you just heat it? Did you do anything else? I think you may have just heated it. That may be part of why we did that one. Okay, so heat also helps to push it to the right. Okay, all right, so. Oh, what alcohol and carboxylic acid would be used to make each of the following esters? I got two. Do you have this page? Did I skip a page? We're going to do the mechanism, so I'm not quite sure where I put it. I know. If there isn't a space, we will add a space. Okay. All right. So you look at this ester, and you're going to synthesize it. Okay. Using the Fischer esterification. So you need to have an alcohol and a carboxylic acid. What part comes from the alcohol? Is it the benzene ring? Am I going to write benzene OH? Okay, can you see the two pieces? Okay, so you're going to break the molecule essentially in half here, right? This is the new bond that's formed. what does this come from? The alcohol. So this one is like the one you did in class where you use the N-propyl alcohol. Okay, so the other side over here is going to be the carboxylic acid. So what is that going to be? Here's your clue. Benzene. Okay, and what's attached to it? Carboxylic acid, right? Okay, did you have to do much more? You had to figure out another one? Ah, see? You should know this already. All right, so how do you do the next one? Where are you going to break the molecule to come up with your two pieces? Yeah, right there. All right, so what is your alcohol going to be? Can you draw it? You can draw it just like it looks. At least if you can get your pen to go to the right spot, you can. Okay, what about the left side? What is that giving? CH3, CH2, carboxylic acid, right? When they're done, we're all drawing it like the sticks. Okay. Okay? Everybody get that so far? All right. It's pretty straightforward. Okay, so how about this one? What alcohol and what carboxylic acid would be used to make the compound below in a Fischer esterification? You go. Can you see the pictures or should I outline them? Are they okay? Andrea says they're okay and she's in there. Are they okay? You can read them? Okay. I don't understand why this program does this. I paste them into any other program and they're just as dark as up. But in this program, it makes them grayed out like that. So look at this. And then we'll go over it. Okay. So where do you bust the molecule in half? Right here. Okay, so this side, because it has the carbonyl in it, is going to become the carboxylic acid. Okay, which ones have the correct carboxylic acid? B and D have the correct carboxylic acid. Okay, what's wrong with A? We didn't even the carboxylic acid. It's screwed up. Okay, what's wrong with C? It has an extra carbon in there. A lot of times people working with rings, they start throwing extra carbons in. Don't be doing that. All right, what about this piece? That's going to be the ethanol, the alcohol. Okay, so that obviously is, this is the only one with both of them correct. Okay. Make as a sense? Oh, I knew it was going to be somewhere. Okay, so we're going to start with, we're going to have our alcohol. And we're going to add it to a carboxylic acid. So here's going to be our carboxylic acid. Okay. Okay. What else is in there besides those two things? H2SO4. You really need that extra acid in there. Could you get it? You maybe could if you were doing a good job of pulling out the water or something. But the acid really, really helps. Okay, so H2SO4 means that we are adding H3O plus. Okay, so what happens first? What do acids do? They add what? Protons, hydrogens to some. Okay, we got a whole lot of lone pairs. Only one spot will get you anywhere. Which spot is it? Yes. Okay, and remember that that is the most negative part on the molecule because this has a resonance form. Okay, that's a resonance arrow. It just doesn't look like one. Where it's this. Okay, so remember, carbonyls are polarized. The carbon end is plus. Okay, right? The O is negative. So that's why it goes there. Okay, now what do we get after that step? Well, we didn't do anything to the alcohol, did we? All right, so let's not worry about it. Here's my benzene ring. Okay, so now I'm going to have a bond from one of the lone pairs on the O to a H, right? And the O is now positive. Are you positive? If you're not, figure it out again. All right, what did we get from the water up, the hydronium ion up there? Come on, I want to go back to purple. Okay, I'm going to get H, O, H, and we added another what to the O? Another lone pair, so that O is now neutral. Okay? Now, by protonating that, that makes this more reactive. Okay? So your nucleophile will thus attack the carbon nucleus. Okay? And then we go out to the O. Okay? But you already know all this, right? Because you did it in the lab. Did you have to write it out? Oh, good. All right, so here's what I had, okay? So now what are we going to do? This O up here is going to have two lone pairs on it, right? There, tried to make it fall. There's my new one, okay? And then I have a bond from here to right, that OH, and then I'm going to have my little carbons. 1, 2, 3. However, whatever they are. Okay. Now, what can you tell me about that O down here? What? It's what? Is that right, the way I have it written? It's missing. A positive on the O. Okay. Okay, now, remember that all the steps in here are equilibrium. So, if you're thinking, well, the lone pair will come back down and that will leave. Yeah, it will. That just takes you back to where you started and we'll do it again. Okay? So, the molecules are, you know, in an equilibrium. Okay? So what will get us somewhere will be getting rid of that proton, okay? There are numerous ways that you can get rid of that proton, okay? Give me one. What did you do in the lab? Did he use the water to do it? Or did he use within the molecule? What? No. Sulfuric acid is what protonated it.
Oh.
Okay, but you're talking about HSO4 minus? Did you use that? Yeah, you could use that. Nothing wrong with using that. Okay, I'm just going to use water. Okay, so we're going to, oops, I like to change colors so that you keep track of what's changing. Okay, so we're going to grab that proton, and where do these electrons go? To the O, to the O. All right, so remember to draw what didn't change. We still have this, we still have this, we still have this. Okay, only worry about where you put your arrows. Okay, what happened to the H2O now? It became, what is H3O plus, aka hydronium ion, right? Okay, and on, so this is our new proton that we put on here. Okay, and then on here we now have another lone pair. Okay, now you know where we're going, right? So what do I got to do to get there? Well, what I got to do is I got to lose water. Okay, so I got to make water by taking an OH and protonating it, okay? Just like we've done a couple of times before. Okay? It doesn't matter which one you pick, okay? So now I'm going to have draw what didn't change. The benzene ring is still there. I can't wait to do benzene. That's another one. Okay, so here's where I had. Hey, can I write P? I'm going to write PRO for the purple group. Okay, that'll make it easy. All right, so now what did I change? Well, the O, and it wouldn't matter which one you pick, by the way, will now have a bond to a hydrogen. And what happened to the H3O plus? What did I get? I got H2O. Okay, what else do I need? What's missing? The thing you all like to miss, the plus on the O. Those charges are important. All right, now how can we get rid of the water? Remember what we did in the Pinacol rearrangement? Oh, look, I'm going to make it red. Okay, these electrons are going to come here and kick out. That's an arrow. Kick out the water. Okay? Just like we did in that Pinacol thing that I showed you a little bit ago. All right, so we're going to do this. Let's see if it'll work. Okay, so now I'm going to have my benzene ring. Draw what didn't change. All right, I'm writing PRO for the purple group. Okay, that H is still on that other O, right? Okay, so now between the O and the C, I have a what? A double bond. And what happened over here? H2O. Okay, what else do I need? That thing that you like to skip. Which is why I'm asking you every time. The what? The oxygen needs a plus charge. Okay, now how do I get to the product? What is the water going to do? I'll use the one that I just made. It's going to pull off the proton, and these electrons are going to go to the O. Man, oh man, the pen is not lined up very good today. It's not lined up very good every day, is what I've noticed. Okay, so notice how you get this. Okay, and what did we get over here? In the very end, we made another hydronium ion. That's why it's acid catalyzed. Okay. Okay. We got it? We're good to go? You're going to be ready for the test to write one out. Don't say no. You've been warned. You don't like words? You like pictures. If a strong acid like sulfuric acid is in your reaction, what is likely to be the first step in organic mechanism? A, H plus leaves the organic molecule. B, something is protonated on the organic molecule by hydronium ion. C, HSO4 minus removes a proton from the organic molecule. D, H2O adds a proton to the organic molecule. E, sulfuric acid removes a proton from the organic molecule. F, hydroxide ion removes a proton from the organic molecule. I gave you F. Okay, what is most likely to be the first step? If you can draw the first step, y'all, I will often give you. Okay. Well, it depends how many steps there are. If there's only 3, you know, but if there's 6 and you only give me 1, I mean, if you give me the first step and you give me the product, that's 2 points. Right? All right. Up to 13. You got to go to 17, so make a pick. Yes, B. All right, I'm up to 71%. Okay. Something gets protonated. What are possible things to get protonated? Oxygen. A double bond can get protonated. A triple bond can get protonated. Okay. On lone pair on a nitrogen, which is something we haven't really seen yet. Lone pairs, double bonds, pi bonds. Okay. I'm trying to get you to be logical. All right, the last thing we have is esters from acid chlorides. This is easier than the Fischer esterification, but oftentimes, why did I write but 2 steps? Oh, well, you usually have to make your acid chloride, and then you have to add the alcohol to it. So it's a little bit extra. Okay, that's what we mean by that. All right, so look at this one down here. N-propylbutyrate. Can you tell me what acid chloride and what alcohol you would use to make N-propyl? Okay, so that's going to be, let's see if I can. 1, 2, 3, 4. 4 carbons. Okay, but what is going to be the acid chloride that you would use? You would use this. Okay, to make that acid chloride, do you remember this? Thionyl chloride and pyridine, what did we use that for? We took alcohols to alkyl chlorides, right? Okay, it was only 2 days ago. Okay, it wasn't even last semester. All right, so it works with these too. Okay, you can also use like the PCl3 and stuff, but you cannot use HCl that way. Okay, you have to use one to special. All right, now what am I going to add to this to get to there? Hmm? Okay. When you do this reaction, you're going to have your acid chloride and you're going to have your alcohol. I'm just going to write R prime, okay? Okay, the alcohol is going to go to the carbon of the carbonyl. Then what happens? Every time you add to a carbonyl, what did I tell you to do? Go what? Go out to the O, out to the O. Okay, always go out to the O. All right. You're going to have a little proton transfer. Okay. We'll just do it internal because that makes us happy. Okay. And then what will happen is you're going to lose the chloride. Okay. And then deprotonate. Okay. So you go out to the O and basically you kick off the chloride. Okay. Because chloride ion is a good leaving group. All right, that's it. We're going to start chapter 13. What else do I have on? Oh, that was, I'm not worried about that. I guess maybe I should talk about that. All right, I'll talk about that. It'll take 5 minutes. And then we'll start chapter. Start.